Calculating skew and latency in VLSI using dimensions. While dimensions can be helpful in estimating skew and latency in a VLSI design, it's not a straightforward calculation. Here's why. Skew and latency are time-based metrics. They are measured in seconds, ns, ps, and depend on the electrical properties of the materials, not just physical distance. Signal propagation delay depends on multiple factors. Wire resistance, capacitance, and the driver strength of sending the signal all contribute to the delay. Layout complexity matters. The actual path a signal takes on the chip can be more intricate than a straight line between 2 points. However, understanding the relationship between dimensions and these concepts can be valuable. Here's a breakdown. 1. Skew and dimension. Imagine two signals traveling on wires with different lengths. The longer wire will likely experience a higher delay, causing the signals to arrive at their destination, flip-flops, at different times. This difference in arrival times is essentially skew. 2. Latency and dimension. Think of a single signal traveling on a wire. The time it takes for the signal to reach its destination depends on the wire's length. A longer wire typically translates to higher latency. While you can't directly calculate precise skew and latency using just dimensions, here are some approaches that incorporate them. Wire length estimation. By estimating the wire length between 2 points based on their placement on the layout, you can get a rough idea of the potential delay difference, skew, for signals traveling those paths. RC delay models. These models consider wire resistance, R, and capacitance, C, to estimate the propagation delay based on wire length. However, they are simplified models and may not capture all the complexities of real-world scenarios. Electronic design automation, EDA, tools are commonly used for accurate skew and latency analysis in VLSI design. These tools take into account the physical layout, material properties, and circuit characteristics to provide more precise estimations. In conclusion, dimensions offer a starting point for understanding skew and latency, but for real-world design, more sophisticated techniques and tools are necessary for accurate calculations. What factors influence standard cell placement in VLSI? Placing standard cells effectively is a crucial step in VLSI physical design. Here are the key factors that come into play when deciding where to put each cell. 1. Timing optimization. Minimize wire length. Shorter wires result in faster signal propagation and reduced delays. The placement tool tries to put frequently communicating cells closer together to minimize wire length on critical paths. Clock network planning. The clock signal needs to reach all flip-flops simultaneously. Placement considers efficient clock tree design to minimize clock skew, variations in arrival time. 2. Power optimization. Reduce power consumption. Shorter wires translate to lower capacitance and less power dissipation during signal switching. Power gating and isolation. Cells with similar power gating requirements, turning power on, off, might be placed close together for efficient power management. 3. Routability. Minimize routing congestion. Cells are arranged in a way that leaves enough space for routing wires between them. Congestion can lead to longer wires and routing challenges. 4. Design constraints. Macro placement. Pre-designed blocks, macros, are often placed first, and standard cells are placed around them considering their pin locations. I/O pad placement. Input-output pads connect the chip to the external world. Their placement influences routing of signals to internal cells. 5. Additional considerations. Cell area and height. Standard cells typically have fixed heights and variable widths. The placement tool considers these dimensions for efficient packing on the chip. Cell functionality. In some cases, placing functionally similar cells together can be beneficial for future design modifications. Finding the optimal balance. There's no single, best, placement solution. The placement tool juggles these factors to achieve an overall layout that optimizes for timing, power, routability, and adherence to design constraints.